Hello students, I hope you all are doing good. Today we are going to discuss NCERT section 10.4 and example 10.1 of chapter Wave Optics. This is the disclaimer. So after this lecture, you will be able to understand the principle of wave superposition, interference, phenomena, and distinction between coherent and incoherent addition of waves, with emphasis on constructive and destructive interference pattern. Okay, so these terms you may have heard in waves, chapter 14th of 11th class. Okay, so principle of wave superposition, what is interference, what is constructive and destructive interference, and the new term is coherent and incoherent addition of waves, or coherent or incoherent sources. Okay, so these things we are going to discuss. So index of topics that we are going to discuss today according to NCERT, example 10.1 and NCERT section 10.4, coherent and incoherent addition of waves. So let's see example 10.1. When monochromatic light is incident on a surface separating two media. Okay, there is a surface which is separating two media, or we can say interface, and we have monochromatic light, means light of one color. Okay, just like red light, like yellow light. Okay, color light of single color, that is called monochromatic light. The reflected and refracted light both have same frequency as the incident frequency. Explain why. Okay, we have discussed that after refraction and reflection, when light enters into another medium, frequency remains same. Frequency in all medium for a particular frequency, particular color of light remains same. So we have to explain why. B part, when light travels from a rarer to denser medium, the speed decreases. Okay, light travels from rarer to denser medium, speed decreases. Does the reduction in speed imply a reduction in the energy carried by the light wave? Okay, will energy also be decreased or reduced while light is traveling from rarer to denser medium? Speed is decreasing. Will energy be decreased or not? Okay, and C part, in the wave picture of light, intensity of light is determined by a square of amplitude of wave. Okay, intensity of light. So what is amplitude of wave? Is the maximum displacement of wave. Okay, intensity is determined by square of amplitude of wave. What determines the intensity of light in the photon picture? When we consider light as when we consider particle nature of light, then which quantity determines the intensity of light? You have to identify that also. So let's see the solution. A part, reflection and diffraction arise through interaction of incident light with atomic constituents of matter. Okay, when if we consider light as a particle, okay, if we consider particle nature of light, then light consists of energy packets called photons. These photons interact with atomic constituents. Okay, electron, proton, and other atomic parts, components. Okay, so reflection and refraction arises through the interaction of incident light with the atomic constituents of matter. So this light causes electron in the material to oscillate. When electron absorb energy from the light, when energy packets called photons that are being absorbed by the electrons, okay, so they made electrons to oscillate. So electrons of that material, of that matter on which light is falling or through which light is traveling, so energy is transferred also, so due to which electrons in the material starts oscillating. Okay, so these oscillating electrons re-emit light. Okay, when they absorb the light, then they start oscillating, and due to the oscillation of electrons, energy is re-emitted, light is re-emitted again. Okay, so these electrons oscillate at the same frequency as the incident light. So oscillations, frequency of oscillations of electron is same as the frequency of incident light. And therefore re-emitted light, since frequency of oscillation is same as incident light and they are re-emitting the light through the oscillations. Okay, so re-emitted light has the same frequency as the incident frequency also. Okay, so re-emitted light can be reflected, or both cases can be considered, reflection and refraction. Okay, so re-emitted light in the case of reflection and refraction has the same frequency as incident frequency, because re-emitted light is producing from oscillation of electron. So frequency of oscillation of electron is same as the frequency of incident light. So that's why re-emitted light is also has same frequency as the incident light. Okay, so energy of light does not decrease. Speed decreases when light travels from rarer to denser medium. Speed decreases. Also wavelength decreases, but frequency remains same. Frequency does not change. Okay, so energy is associated with frequency, not with speed or not with wavelength. Wavelength and speed changes. When it goes from rarer to denser medium, speed decreases. Also wavelength decreases by same proportion, such that frequency remains same. So energy of light does not decrease when its speed decreases in denser medium. Why? So in photon picture of light, when light is considered as particle, so particle nature, when we consider particle nature of light, then energy of light is given by energy of photon, and energy of photon is given by E equal to h nu. Okay, it depends on only h is the Planck's constant. Okay, it is a constant, but energy also depends on frequency of the light. Okay, so it only depends on frequency. So since we know that frequency does not change when light travels from one medium to another, that's why energy will not change. So frequency of refracted light does not change, so energy of light does not decrease when its speed decreases in denser medium. Okay, so energy and frequency remain same, only speed and wavelength changes. Now, in photon picture of light, intensity, in the case of when we consider wave nature, or we can say wave picture of light, then intensity is determined by square of amplitude of wave. Okay, amplitude we will see now in the further slides. Okay, so square of the amplitude. But in the photon picture of light, intensity is determined by number of photons passing through a given area per unit time, which is also called photon flux. Okay, so intensity is determined by number of photons passing through a given area per unit time. Okay, which is also called photon flux. Got it? So now we will understand the principle of superposition. Okay, so figure superposition of two waves. It is given one wave having displacement. So what is the displacement? Okay, at any instant, the wave, any particle position with respect to x-axis in the y direction. That is the displacement at that instant of the wave. Okay, and maximum displacement is called amplitude. Okay, so you can see this wave, this outer wave, which is represented by bold font. So its maximum displacement along y-axis, this is known as amplitude of the wave. Got it? So what is principle of superposition? When two or more waves, so these are two waves. This is first wave having displacement at any instant y1, and this is second wave having displacement at an instant y2. Okay, so when two or more waves overlap at a point, so they are overlapping. Crest of one wave is lying on crest of another. Trough of one wave is lying on another. Okay, but it is not compulsory that always crest will lie on crest or trough will lie on trough. Okay, it can be in any orientation. Okay, so principle of superposition. According to principle of superposition, when two or more waves overlap at a point, the resultant displacement produced by the number of waves is the vector sum of displacements produced by each of the waves. Okay, so resultant displacement. So you can see one more wave. This is a resultant wave due to the superposition of these two waves. This is the resultant wave. So resultant displacement of this wave will be equal to the vector sum of displacements of these two waves produced by each of the wave. Got it? So why we are taking vector sum? Because the displacement of these two waves can be in any direction. Okay, in this particular diagram we are considering in the y direction, or further we are doing derivation. Okay, we are going to do derivation also. So we will consider the displacement in the y direction, but displacement can be in any direction. So due to which we are taking vector sum of displacements produced by each of the waves. So for two waves superpositioning or superposition traveling along the same direction, we can write, so they can be traveling in the opposite direction also, but we are considering traveling in the same direction. So why we have not taken vectors? Because for simplicity we have taken displacement along y direction, so in same direction. Okay, also waves are moving in same direction, displacements also are in same direction. That's why they can be simply added. Displacements due to each wave can be simply added. But if they are in different directions, okay, if one wave is in y direction, displacement of one wave is in y direction, along y axis, and displacement of another wave is along some another axis, or suppose that axis. Okay, then we have to take the vector sum for the resultant displacement. Now displacement of both waves are along y axis, that's why they are simply added. So yxt, displacement of resultant wave at any time at any position along x axis, is represented by, so y is the function of x and t both. Okay, it is a function of x and it is function of t, function of position and time. Okay, which is equal to y1 xt plus y2 xt. So that xt in bracket representing that y displacement is function of position and time both. So position along x axis. Okay, so means here, if I am taking any arbitrary position here, so at this x value, what is the displacement of this wave along y axis? Okay, so that is the dependence of displacement on position along x axis and also on time, after which time. Okay, so this is the wave, this is one wavelength represented, another one wave is represented. Okay, so for same point, means if I am taking this point, and again when it is repeating, again I am taking this point, so x will be different. Okay, also time will be different, but y will be same. Okay, y is here at this point 0. Okay, so where y1 xt and y2 xt is the displacement at position x and time t of wave 1 and 2 respectively, and yxt is the resultant displacement at position x and time t. Okay, now to understand crest and trough in a wave. So you can see in the diagram, okay, the maximum displacement in the positive direction, okay, is called crest. So this point, okay, maximum displacement is amplitude, but is the highest point is called crest and lowest point is called trough. Okay, and distance between two troughs and distance between two crests is known as wavelength. Okay, So what is crest? Imagine a wave moving through water. Crest is the peak or highest point of the wave. This point. Okay, above the undisturbed water level. If water is undisturbed and then it is disturbed, then waves are formed, ripples are formed. So the peak, the highest point of that wave from that is considered that x-axis as undisturbed water level. Okay, now water is disturbed, so waves are formed. So this highest point is called crest. Okay, above the undisturbed water level. It represents the maximum displacement of medium. Okay, water in this case, in the upward direction. Which direction? Upward, positive direction. And what is trough? Is the lowest point of the wave below the undisturbed water level. Lowest point. Okay, so it represents the maximum displacement of the medium in the downward direction. That is negative direction. So what is interference? Okay, so corresponding to this trough and crest, there is maximum displacement. Okay, which is known as amplitude also. So it is interference, phenomenon in which two or more waves superimpose to form a resultant wave of greater lower amplitude. Okay, so in which two waves superimpose, okay, they combine to form a resultant wave of either greater amplitude or either lower amplitude. Okay, so it depends on the type of interference. If the interference is constructive, then amplitude of the resultant wave will be increased. If interference will be destructive, then amplitude of the resultant wave will be decreased. Okay, so distribution of energy is must. When two waves combine, when two waves superimpose, then energy is distributed among the two waves and it is redistributed again. Now to understand interference pattern produced by the superposition of two waves. So figure 10.8a, two needles oscillating in phase in water represent two coherent sources. B part, the pattern of displacement of water molecules at an instant on the surface of water showing nodal N no displacement and antinodal A maximum displacement lines. Okay, you can see in the B diagram. So these A points, this is antinodes, means maximum displacement. So these are the point of maximum displacements. So here you can see two waves are combining. So constructive interference is going on. So these are the points of antinodes, maximum displacement. And these. So two waves are not superimposing perfectly. So this is the destructive interference. So nodes are forming on these points. Okay, no displacement. So consider two needles S1 and S2 in the A diagram moving periodically up and down in an identical fashion in a trough of water. What is trough of water? It is not trough of wave. It is trough of water means some container. Okay, some large container made of concrete or anything in which water is filled. So that is trough of water. So consider two needles S1 and S2 and moving periodically up and down. So it is moving inside water and then again with needle is being dipped in water and then again it will be taken out. Then again it is dipped in water, again taken out. Okay, so it is moving periodically up and down in the trough of water. So they produce two water waves. So due to the needle motion inside the water and outside periodically, so they produce two water waves and at a particular point P. Okay, so the phase difference between the displacement produced by each of the wave does not change with time. Okay, so they are moving periodically up and down. Okay, and at the same time, so phase difference between the displacements produced by each of the waves. So they are producing waves. So these needles, the motion of these needles producing wave. Okay, so the phase difference at P point phase difference between two waves produced by S1 and S2 respectively is not changing with time at P point. Okay, so when this happens, the two sources are said to be coherent. When phase difference at any point, okay, phase difference between two waves or phase difference between two waves produced by two different, means two sources, is not changing with respect to time. Either the phase difference is zero, either phase difference is constant. That means it is not changing with respect to time. Then these two sources are said to be coherent. Okay, so to understand coherent sources, so what are coherent sources? Two sources are said to be coherent if they emit light waves of same frequency and have a constant phase difference between them, either zero phase difference or constant phase difference between them. Okay, so the waves that are producing from these sources will have zero phase difference between them or constant phase difference with time. That means phase difference is not changing with respect to time, and also they emit light waves of the same frequency. Okay, so these conditions are applicable on coherent sources. Okay, so two sources are only said to be coherent if they emit light waves of same frequency or they have a constant phase difference or zero phase difference between them. So figure 10.8b shows the position of crests, solid circles and troughs, dashed lines at a given instant of time. Okay, you can see in the diagram. So these solid circles, these are representing the crests, and dashed lines, so these solid circles, these are representing crest, and dashed circles, these dashed circles. So it is bit complicated diagram. So these dashed lines you can see, these are dashed circles, they are representing trough at a given instant of time. Okay, so figure 10.8b, the pattern of displacement of water molecules at an instant on the surface of water showing nodal N and antinodal A. So I have already explained that you can see these waves, these crests. So crest is lying on crest of another wave. So they are superimposing. Okay, this is represented by these points. These are known as antinodals. Okay, antinodes, or we can say that is having maximum displacement. And when crest of, you can see when crest of one crest is lying on the trough, you can see this is dashed line. This is a bit complicated diagram, but you can see this is the dashed line and it is meeting the solid line. That means trough, one crest is lying on trough of another wave. Okay, so due to which destructive interference is happening and due to which no displacement. Okay, means zero displacement and nodes are forming. Okay. So consider a point P for which S1P equal to S2P. So we are considering one point which is equidistant from both the sources S1 and S2. What are these sources? These are 2 points on which needles are periodically moved up and down. So these are 2 points on the water surface. Okay, so you can consider a P point which is equidistant from this S1 and S2 source. So S1 and S2 are coherent sources in this case. Okay, because P phase difference at P point is not changing with respect to time. Okay, so because the distances are equal, that means waves from both needles take the same time to reach the point P. So P point is equidistant from S1 and S2. So time required by the waves to reach this P point from S1 and S2 is same. So if the needles start moving together in phase, so if we are moving needles periodically up and down in the same time we are dipping them in the water, and same time we are taking them away, taking them out from the water surface. Okay, so that means they are moving together, they are moving in phase. So their wave will also arrive together in phase at P point. So the waves produced by both needles will reach the point P at same time, and also they will reach in phase because we are moving these needles together in phase. So waves will also be in phase at P point. That means phase difference is 0 in this case. Okay, so if the displacement produced by source S1 at P point is given by, so what is the displacement produced? Y1 equal to A cos omega t. So what is the equation of wave? We have discussed in waves chapter. So Y equal to A cos kx minus omega t. Okay, so why we are not taking kx? Because we are taking the distance entirely. So P point is taken at x equal to 0. Okay, so P point is considered at x equal to 0, means at y axis. That's why x becomes 0. So our equation is A cos omega t is simplified to. So for simplification we have done that. Okay, we have not considered the x position. We are considering P point on y axis. So y1 equal to A cos omega t. So this is the equation of wave. So now displacement produced by the source S2 will also be given as y2 equal to A cos omega t. Since they are in phase, there is no phase difference. So phase difference is 0. That's why y1 is also A cos omega t, y2 is also A cos omega t. Amplitude is also same. Okay, we are moving these needles together. So amplitude also same. So where A is the amplitude in the wave, same in this case. So resultant of displacement of both waves at P would be, so now we find the resultant. Resultant can be found using superposition principle. Okay, superposition principle means the resultant displacement of the wave is represented by the vector sum of displacement of each wave at that time. Okay, since we are considering the displacement along y axis only, so they can be directly added. So y equal to y1 plus y2. Why we are not taking vector sum? Because they are along y axis, so they can be directly added. If direction of displacement will be different, then we will apply vector algebra. Okay, so y1 plus y2, which is A cos omega t plus A cos omega t, which is equal to 2A cos omega t. Okay, so where 2A represents the amplitude of resultant wave. So intensity in wave theory is proportional to the, okay, this thing we have discussed. So amplitude, now you know what is amplitude. Maximum displacement of a wave is known as amplitude. Okay, so intensity of wave is given by, so intensity in wave theory is proportional to the square of amplitude. Okay, so resultant intensity will be given by, so resultant intensity of resultant wave will be proportional to the amplitude of that wave. So amplitude of resultant wave is represented by, so displacement, resultant displacement of resultant wave is given by y equal to 2A cos omega t, where 2A is the amplitude of resultant wave. So intensity will be proportional to 2A square, that is 4A square. Okay, so intensity of resultant wave will be 4 times the intensity of each wave. Okay, so I naught represents the intensity produced by each one of the individual sources, and I naught is proportional to A square. So I naught will be the resultant, I naught will be the intensity produced by the each wave. Okay, and I naught is proportional to amplitude of each wave. So amplitude of each wave is A. So it is proportional to A square, and amplitude of resultant wave is 2A. So that's why intensity of resultant wave is proportional to 4A square. Okay, so while taking the ratio I proportional to 4A square, and I naught proportional to a square, the ratio will be I upon I naught equal to 4. So I will be equal to 4 I naught. Okay, so intensity of resultant wave will be equal to 4 times the intensity of individual sources or wave. Okay, so let's see constructive interference. So when two waves of same frequency overlap and crest of one wave aligns with the crest of another wave, or trough aligns with trough. You can see in the diagram, crest is lying on the crest of another wave and trough aligns with the trough of another wave. Then constructive interference occurs, due to which the amplitude of the resultant wave will be increased. So waves add together to create a wave with greater amplitude, like that, shown in the diagram. So this results in higher intensity at those points where the waves combine constructively. Okay, so since amplitude is increasing of the resultant wave, so intensity will also be increased, because intensity is proportional to amplitude square. So amplitude is increasing of the resultant wave, that's why intensity will also increase. So this results in a higher intensity at those points where wave combine constructively. So this is known as constructive interference. Now we will understand interference pattern produced by superposition of waves. So now you can consider any Q point. Okay, so distance from S1 source is S1Q and distance from this S2 source is S2Q. So now consider a point Q as represented by figure 10.9a, for which S2Q minus N1Q equal to 2 lambda. So from this point Q, S1 is separated by 7 lambda. Lambda is the wavelength. Okay, so it is separated by 7 lambda and distance between S2 and Q is 9 lambda. So S2Q minus S1Q is 2 lambda. So let's consider a point Q for which S2Q minus S1Q, so the path difference will be 2 lambda. Okay, so wave emanating or emerging or beginning from S1 will arrive exactly 2 cycles earlier than the waves from S2 and will again be in phase. Okay, so waves emerging from this S1 will reach 2 cycles earlier, because difference is 2 lambda. 1 lambda is 1 wavelength, means 1 cycle. Okay, 1 cycle, 1 wavelength. So it will reach 2 cycles earlier than waves emerging from S2. Okay, so again it is in phase. What is meant by phase? We have discussed in alternating current also. Okay, so if you can see, this wave is starting from this point and this is complete wavelength here. Now again, it is starting from that point. It is repeating its motion. It is repeating its value. Okay, so that is called periodicity. Okay, so what means it is in phase? Means they are both at same situation. So after that, it will reach at 0. So after completing 7 cycles, it will reach at this axis, and also after completing 9 cycle, it will reach at this 0 displacement. Now after that point Q, they will start from 0 to maximum. Both will go 0 to maximum at same time and maximum to minimum at same point. That means they are in phase. Okay, so let the displacement produced by S1 is given by y1 equal to a cos omega t. Okay, so for S1 displacement, equation of displacement, we can write y1 equal to a cos omega t. But now they are not having same phase. Okay, so they are in phase, but they have some constant phase difference. So now S2Q is larger than S1Q by 2 lambda. That's why S2q minus S1q is 2 lambda. Okay, due to this path difference, there will be a phase difference. So they are in phase, means both waves emerging from both sources are reaching their maximum and minimum point at the same time. That means they are in phase, but they have some constant phase difference. They have constant path difference. So what is the path difference? 2 lambda. So there will be a phase difference between two waves also. So what is the phase difference? So we can find the phase difference if we know the path difference by the formula. So phase difference is equal to 2 pi upon lambda multiplied by path difference. So path difference is 2 lambda. That means phase difference is represented by phi, and it will be 2 pi upon lambda multiplied by, what is path difference here? 2 lambda. So it will represent 4 pi. So phase difference. So we also know this is one cycle representing 2 pi. So it is, so what is the path difference? 2 lambda. So 1 lambda represents 2 pi. So 2 lambda represents 4 pi. This is also the, you can find using formula 2 pi upon lambda multiplied by 2 lambda, which is equal to 4 pi. So this is the phase difference of these two waves starting from S1 and S2. Okay, so phi is equal to 4 pi. This means a path difference of 2 lambda corresponds to a phase difference of 4 pi. So now y1 equal to a cos omega t. Then the displacement produced by S2, that is y2, it will be represented by, amplitude is same, so a cos omega t, but now there is a phase difference. So omega t plus 4 pi, okay, or minus 4 pi, we can write. So y2 is equal to a cos omega t minus 4 pi. So this is the phase difference, which is equal to a cos omega t again. Why? Because a theta minus 4 pi equals to a, which is equal to cos minus 4 pi minus theta. So we are taking negative sign as common. So theta minus 4 pi will become minus 4 pi minus theta. Okay. So now cos will consume the negative sign, which is in the argument. So cos minus theta is cos theta. So cos minus 4 pi minus theta will be cos 4 pi minus theta. Okay. So cos 4 pi minus theta will be, so conversion is going on with the 4 pi. That means cos 4 pi minus theta will remain as cos theta. But minus cos theta or plus cos theta, you have to see the quadrant. So 4 pi minus theta. So theta, some theta is subtracting from 4 pi. That means in fourth quadrant. So that function is in fourth quadrant. So in fourth quadrant cos is positive. So these are trigonometric basics I am explaining here. Okay. So cos 4 pi minus theta representing cos theta. That's why cos omega t minus 4 pi represents, will be equal to cos minus in bracket 4 pi minus omega t, which is equal to cos 4 pi minus omega t. So it will be equal to cos omega t. That's why a cos omega t minus 4 pi equals to a cos omega t. Okay, this means y1 equal to y2. And two displacements are once again in phase. And intensity will again be 4I naught, giving rise to constructive interference. Okay, so y1 is also a cos omega t, y2 is also a cos omega t. So resultant displacement will be 2a cos omega t. So intensity will again be 4 times the intensity of each wave, because intensity is proportional to amplitude square, giving rise to constructive interference. Now consider a point R for which S2R minus S1R is equal to minus 2.5 lambda. Okay, so S2R is 7.25 lambda. So we are taking arbitrary values. So S2R is equal to 7.25 lambda minus S1R, which is 9.75 lambda. So it will represent, so after subtracting, it will become minus 2.5 lambda. Okay, so path difference is minus 2.5 lambda. So waves originating from S1 will arrive exactly 2.5 cycles later than waves from S2. Okay, so S2 is ahead of S1. So S2 waves originating from S2 will reach earlier than waves originating from S1. How much earlier? 2.5 cycles earlier. Okay. So let the displacement produced by S1 is y1 equal to a cos omega t. Okay, now we will find the y2. So since there is a path difference of 2.5 lambda between the two waves, so there will be a phase difference of, so if path difference is 2.5 lambda, we can find the phase difference. So phase difference will be equal to 2 pi lambda multiplied by path difference, which is 2.5 lambda, which is equal to 5 pi. So phase difference is 5 pi. So y1 is equal to a cos omega t. Then the displacement produced by S2 will be given by y2 equal to a cos omega t plus 5 pi. Why plus? Because it is reaching ahead of S1. So phase difference is, initial phase is plus 5 pi. Okay, so y2 is equal to a cos omega t plus 5 pi. So it is leading, we can see. That's why phase difference is added. So a cos omega t plus 5 pi. So cos 5 pi plus theta. This function will lie in cos 5 pi plus theta. So this argument 5 pi plus theta. So this angle lies in which quadrant? Third quadrant. Okay, so in third quadrant cos is negative. That's why minus cos theta. And conversion is done by integral multiple of pi. That's why cos will result in cos. But sign, we can decide the sign negative or positive by the quadrant of angle. So 5 pi plus theta lies in third quadrant. That's why minus cos theta. So cos omega t plus 5 pi will be minus cos omega t. So y2 will be minus a cos omega t. So y1 is a cos omega t, y2 is minus a cos omega t. So two displacements are out of phase. And we can find the resultant. So two displacements will cancel out to give the zero intensity. So if we find the resultant displacement y equal to y1 plus y2, it will result in 0. That means displacement, it will give the resultant wave with 0 displacement. That means 0 intensity. Okay, so y equal to y1 plus y2 will give us a cos omega t plus minus a cos omega t, which is equal to 0. So since displacement is 0, that means intensity of resultant wave will be 0. This is known as destructive interference. Okay, so it is represented by this. When crest falls on trough and trough falls on crest. So destructive interference means when two waves combine in a way, their amplitudes cancel out each other. Okay, resulting in a wave with a reduced amplitude or even no amplitude. Okay, it is not the case that every time amplitude will be 0 or displacement will be 0. But when displacement is decreased, then we can say destructive interference is occurring. Okay, it is not always that displacement will be equal to 0. Resultant displacement will always not be equal to 0. It will be reduced in the case of destructive interference, and complete cancellation or resultant displacement equal to 0 is one of the case. Okay, so or even no amplitude at the point of interference. This happens when crest of one wave aligns with the troughs of another wave. So if we have two coherent sources S1 and S2 vibrating in phase, then for an arbitrary point P, if the path difference S1P minus S2P, then if path difference is integral multiple of lambda, then we can say constructive interference. Okay, we have taken the integral multiple 2 in the case. So that was the case of constructive interference. Okay, we took the path difference 2 lambda. For that, we came to conclusion that This is the case of constructive interference. Okay, so if two coherent sources S1 and S2 vibrating in phase, then for arbitrary any point P, if the path difference is S1 P minus S2 P equal to n lambda, which is integral multiple of wavelength, where n is equal to 0, 1, 2, 3. Okay, equation 10.9. So then we will have a constructive interference, or resultant intensity will be 4I naught. Okay, this is the maximum resultant intensity. Okay, this is not always the case. So maximum resultant intensity will be 4I naught if I1 equal to I2 equal to A. This is the case when amplitudes are same. If amplitudes are I1, if amplitudes of both the waves, both the individual waves is same, then intensity will be 4I naught. Otherwise, it will be less than 4I naught or greater than I naught. Using relation phase difference equal to 2 pi by lambda into path difference, we can find phase difference for the constructive interference. So phase difference will be equal to 2 pi upon lambda multiplied by n lambda. So n lambda is a path difference for constructive interference. So phase difference for constructive interference will be 2n pi, which is even integral multiple of pi. Okay, so for constructive interference, phase difference between two waves originating from two coherent sources will be or should be even multiple of pi, even integral multiple of pi, that is 2n pi. Okay, so on the other hand, if P point is such that the path difference, now we will discuss about destructive interference. So if P point is such that the path difference is odd integral multiple of lambda by 2. Okay, so S1P minus S2P equal to 2n plus 1 lambda by 2, equation 10.10. So then we will have a destructive interference and resultant intensity will be 0. And always resultant intensity will not be 0. Resultant intensity will be 0 if amplitude of both the waves that are superimposing will be same. That is A1 equal to A2 equal to A. Okay, so required condition in the terms of phase difference. So in the terms of phase difference for destructive interference, phase difference should be 2 pi upon lambda multiplied by 2n plus 1 lambda by 2. Okay, so phi, that is phase difference, will be equal to 2n plus 1 pi, where n equal to 0, 1, 2, so on. Okay, so 2n plus 1, put 0, it will be pi. Put 1, it will be 3 pi. Okay, so phase difference should be odd integral multiple of pi for destructive interference. So for destructive interference, phase difference should be odd multiple of pi. And for constructive interference, phase difference should be even multiple of pi. Okay, so this figure, what it is representing? It is representing the locus of points where S1P minus S2P is equal to lambda plus minus 2 lambda or plus minus 3 lambda. Okay, for constructive interference. So for any arbitrary point G, figure 10.10, let the phase difference between the two displacements be phi. Now we are not specifying the phase difference as 5 pi or 4 pi. Okay, so now phase difference will be anything, phi, for any arbitrary point G. So if the displacement produced by S1 is given by y1 equal to a cos omega t, then displacement produced by S2 will be y2 equal to a cos omega t plus phi. Okay, we have discussed specific cases, that is omega t plus 4 pi or omega t minus 4 pi, and another case omega t plus 5 pi. Now phi is anything. Okay, any arbitrary value for any arbitrary point G. So y2 is equal to a cos omega t plus phi. So resultant, we are going to generalize the formula. So the resultant displacement will be given by y equal to y1 plus y2. That is a cos omega t plus phi. So we are going for generalized formula, not for specific value. So y is equal to a cos omega t plus phi. So resultant displacement, we are finding the generalized formula for resultant displacement of a wave. So using identity cos A plus cos B, which is 2 cos A plus B upon 2 cos A minus B upon 2. So A will be taken common. Okay, so cos A plus B, cos omega t plus phi. So A here is omega t and B here is omega t plus phi. So 2A cos omega t plus phi upon 2 cos omega t minus phi upon 2. So it will be equal to 2A cos omega t plus phi by 2. Okay, so 2 omega t plus phi by 2 means omega t plus phi by 2. And cos minus phi by 2, and cos will consume the negative sign. So that's why cos phi by 2. Okay, so after rearranging, y equal to 2A cos phi by 2 cos omega t plus phi by 2. So constant term. So phi is the phase difference. Okay, it is not time dependent. For the coherent sources, we are talking about coherent sources. So phi is constant phase difference. So phi is constant, amplitude is constant for a wave. So 2A cos phi by 2, this is a constant term, represents the amplitude of the resultant displacement. We have discussed specific cases for which maximum amplitude is 2A and minimum amplitude is 0. But this is the generalized case for any phase difference. So constant term 2A cos phi by 2 represents the amplitude of the resultant wave. And cos omega t plus phi by 2, this is a variable term. Okay, so intensity, we know that square, it is proportional to square of amplitude. Therefore, intensity of resultant wave will be. So intensity is proportional to 2A cos phi by 2. Now, amplitude of resultant wave is represented by 2A cos phi by 2. So intensity is proportional to 2A cos phi by 2 square. Okay, and intensity of individual wave is proportional to A square. Okay, so that is I naught. I naught proportional to A square. So we are taking ratio. So I upon I naught will be 4 A square cos square phi by 2 upon A square. So A square and A square will get cancelled out and I naught will go in the right side of the equation. So it will become I equal to 4 I naught cos square phi by 2, which is equation 10.11. So this is the formula of intensity when amplitudes of two superimposing waves are equal. So since maximum value of cos square phi by 2 will be 1. Okay, so this is the case now. We have taken the maximum intensity. When waves of same amplitude and zero phase difference superimpose, then intensity is equal to 4 I naught. That is the case when cos square phi by 2 is 1. Okay, so then I max will be 4 I naught. When cos square phi by 2 is equal to 1, that means phi by 2 is equal to 0 degree. Okay, that means phi is 0 degree. When phase is 0 or even integral multiple of pi, that means 2 pi. When phi is 2 pi, then 2 pi upon 2 will pi. So cos pi is also 0. Cos pi is again 1. Minus 1, and its square will be 1. Okay, so for even integral multiple of pi, that phase difference or zero phase difference will result in maximum intensity. That is I max equal to 4 I naught. Okay, so for phi equal to 0 plus minus 2 pi plus minus 4 pi corresponds to condition of maximum, or we can know it as constructive interference. Now for destructive interference, so I equal to 4 I naught cos square phi by 2. For destructive interference intensity, resultant intensity is 0. When resultant intensity will be 0? When cos square phi by 2 will be equal to 0. Okay, so if cos square phi by 2 equal to 0, that means phi by 2 is equal to 90 degree. Okay, that means phi by 2 is equal to 90 degree and phi equal to 180 degree, means pi. Okay, you can see pi, or any odd integral multiple of pi. If phase difference is any odd integral multiple of pi, then destructive interference will occur. Okay, so on the other hand, if phi is equal to plus minus pi, plus minus 3 pi, plus minus 5 pi, then I will be equal to 0. That is the condition of minimum. That is destructive interference. So now if two sources are coherent, if the two needles are going up and down periodically and at the same time, okay, then the phase difference phi at any point will not change. Okay, these are coherent sources, so phase difference will be 0 either or constant at any point. So, and we will have a stable interference pattern, that is positions of maxima and minima will not change with the time. So position of constructive interference, position of antinodes and nodes will not change with time. Position of constructive interference and destructive interference will not change with time. Okay, that means position of maxima and minima will not change with time. However, if two needles do not maintain a constant phase difference, then interference pattern will also change with time. So if there is the phase difference between the two needles, oscillation of two needles in the water is changing with respect to time. So interference pattern, that maxima and minima, that antinodes and nodes will change. Okay, they will change their position with respect to time. So if the phase difference changes very rapidly with time, the positions of maxima and minimum will also vary rapidly with time. Positions of nodes and antinodes will change rapidly with time, and we will see a time average intensity distribution. So we will not see the maxima and minima. So the intensity, now intensity is not 4I naught maximum intensity and minimum intensity 0. Okay, or intensity will not increase or decrease. So we will see a time average intensity distribution. Okay, so when this happens, we will observe an average intensity at all points. So at all points, there will be average intensity. Okay, when we see at constructive interference, intensity is 4I naught. And at destructive interference, intensity is 0. When amplitude of individual waves are same. Okay, but in the case of incoherent sources, when the phase difference between the waves originating from that sources is changing with respect to time, then we see a time average intensity distribution. Okay, so we will observe an average intensity at all the points. So what is that average intensity? 2I naught. At all points we will observe average intensity of, means there we will not see the interference pattern, that is maxima and minima. Consecutive maxima and minima will not see. We will see the some uniform surface. So this means intensity just add up scalarly. I equal to I naught plus I naught, which is 2I naught. They do not interfere. We will not see interference pattern. So let the displacement of two waves of amplitude A1 and A2 be represented by y1 xt equal to A cos x kx minus omega t and y2 xt equal to A2 cos kx minus omega t plus phi. Okay, so phi is the phase difference assumed to be constant with time. Now we have taken different amplitudes. We have also considered position. We are not taking these displacement along y direction only. Okay, we are not considering x equal to 0. Okay, so when these waves superimpose to give a new wave of amplitude A, then resultant amplitude is given by. So if amplitude is also different of two waves, then resultant amplitude will be given by A square equal to A1 square plus A2 square plus 2A1 A2 cos phi. Okay, if phase difference is also different, okay, and amplitude is also different, then resultant amplitude of a resultant new wave is given by A square equal to A1 square. A1 is the amplitude of first wave, A2 is the amplitude of second wave, and it is given by resultant amplitude capital A is given by capital A square equal to A1 square plus A2 square plus 2A1 A2 cos phi. Phi is the phase difference between two waves. So resultant intensity is given by, so since intensity is the amplitude of, is proportional to the square of amplitude. Okay, so we know that resultant amplitude capital A square is given by A1 square plus A2 square plus 2 root A1 square A2 square. So this is 2A1 A2. We are modifying it. We are writing it root A1 square A2 square cos phi. So intensity will be I. So I is proportional to capital A square. So A square can be written as I, and A1 square is I1, A2 square I2 plus 2 root A1 square can be written as I1, A2 square can be written as I2, and cos phi. So intensity relation will be this. Okay, so where I1 proportional to A1 square and I2 proportional to A2 square, these are the intensities of the wave 1 and 2 respectively. Okay. So there is a derivation of this. Okay, so I can be written as I proportional to capital A square, and we can write I equal to K A square, and also we can write I1 equal to K small A1 square. I2 can be written as K A2 square after removing proportionality sign. Okay, and then K and K on the both sides will get cancelled out, and it will result in I equal to I1 plus I2 plus 2 root I1 I2 cos phi. Okay, so for incoherent sources, so sources for which phase difference phi changes randomly and rapidly with time, so cos phi term in I equal to I1 plus I2 plus 2 root I1 I2 cos phi average to 0 over time. Okay, so phase difference is changing rapidly and randomly with respect to time. So cos phi will be average to 0 over time. So resultant intensity will be simply the sum of the individual intensity. That is, that term 2I1 I2 cos phi will be 0, and I1 plus I2 will remain as it is. So I will be equal to I1 plus I2. This is simply the formula for intensity in the cases of incoherent sources. So two independent sources of light, like two light bulbs, are always incoherent. So two independent sources are always incoherent sources. Now let's see summary. Principle of superposition: total displacement equal to sum of individual wave displacements y equal to y1 plus y2. Two waves traveling in same direction, y1 equal to a1 cos kx minus omega t and y2 equal to a2 cos kx minus omega t plus phi, where phi is phase difference. Okay, resultant intensity I equal to I1 plus I2 plus 2 root I1 I2 cos phi, where I is proportional to, and resultant intensity is proportional to square of resultant amplitude. Coherent sources, same frequency waves with constant phase difference. Constructive interference, when path difference delta p is equal to integral multiple of lambda and phase difference phi is equal to even integral multiple of pi, giving I max. So I1 plus I2 plus 2 root I1 I2 cos phi. We can write I1 as root I1 square or I2 as root I2 square, and this will become, so this is maximum I max. So it will be root I1 plus root I2 square, which is equal to 4I naught. Maximum intensity means when constructive interference happens, means phi is 2 and pi. So for that, cos phi will become 1. Destructive interference, when cos phi will become 0. Okay. Sorry, when cos phi will become negative. So when path difference delta p is equal to 2n plus 1 lambda by 2 and phase difference is phi equal to 2n plus 1 pi. Okay, so which is pi, 3 pi, 5 pi. So for pi, 3 pi, 5 pi, cos phi is minus 1. Okay, so after simplifying, it will become I minimum root I1 minus root I2 whole square, which is equal to 0. When intensity of both the waves is equal to I naught. It is only 0 when intensity of both the waves is same. It is equal to 4 I naught when intensity of I max is equal to 4 I naught when intensity of both waves is equal. Okay. Otherwise, it is not equal to 4 I naught. Otherwise, I minimum is not equal to 0 if both intensities of both waves, individual waves, is not same. Okay. Incoherent sources, random phase difference between the waves, and phase difference is changing with respect to time, resulting in I equal to I1 plus I2. That is averaged intensity. Practice questions. For constructive interference between two coherent waves, the path difference should be lambda by 2, lambda, n lambda, 2n plus 1, lambda by 2. If two coherent sources of equal intensity I naught interfere constructively, the resultant intensity will be I naught, 2 I naught, 3 I naught, 4 I naught. The phase difference for destructive interference between two waves should be 2 pi, pi, 4 pi, any odd multiple of pi. If two waves of intensities I1 and I2 from incoherent sources overlap, what is their resultant intensity? And last question, for coherent sources, what is the condition for destructive interference in the terms of path difference? So thank you. This is all about today's lecture. I hope you enjoyed the session. Thank you.